Okay, let me see here. All right, so there are only two of us here, and one of us is muted. Don't know if he can hear me, but I'm going to commence with this class anyway. And if anybody decide to come in, then they can just come in and pick up from where they started attending this class. So the last time we were here, we were introduced to certain equations concerning waveform and the relationship between the wavelength of the wavelength and the velocity and mass of a moving particle according to the de Broglie equation and so on. So what I've decided to do, and you should have seen this when I posted this in the announcements on Tuesday, I posted these questions, which I'm going to, hold on, I'm going to share my screen. And which one is it? I think this is it. Okay, so these questions are the ones that I posted on Tuesday. And as I think I said during the announcement, we'll be going through these questions in an effort to expose you to the type of questions that you could be facing in a future test or exam. So what I'm going to do is I'm going to go to my writing pad here. I'm going to assume that you have the questions at hand so that you can follow along with me as I go through solving these problems. Now, there are a couple of equations you'll be using in this particular group of questions. One is C is equal to lambda times nu, which relates the speed of light to the wavelength and the frequency of the radiation. Then there is lambda is equal to h over mv, right? Lambda is the wavelength, h is Planck's constant, m is the mass of the particle, and v is the velocity. And the last one would be E is equal to h nu. And there's another one that just comes to mind, which I think will be also involved in at least one of these questions, which would be, well, there are two forms. Delta E is equal to minus RH times 1 over NF squared minus 1 over NI squared. And then the other form of this equation, which is, let me put a line here, 1 over lambda is equal to minus RH times 1 over N squared F minus, move this out of the way, minus 1 over Ni squared. And if you recall, if you're using this form of the equation, RH is going to be equal to 2.18 times 10 to the minus 18 joules. And if you're using this form of the equation, it's going to be 1.10 times 10 to the, oh gosh, I think it's 7 meters to the minus 1. Let me do a quick check just to make sure that I have that right. 1 minute here. Okay. Yes, that's right. Okay, so those are the equations we'll be using in answer to the questions that I've posted on Tuesday, I'm sorry. So the first question, I'm going to bring up here on my other laptop. The first question is, it says an FM radio station broadcast at 95.5 megahertz. Calculate the wavelength of the corresponding radio waves, all right? So the equation that you'll be using is the first one that I mentioned here, but the question is asking for the wavelength. So we'd have to rearrange this to get the wavelength expression, which is lambda is equal to C over nu, all right? So C is 3.00 times 10 to the 8 meters per second divided by the frequency. and they gave the frequency as 95.5 megahertz. However, we have to convert that to hertz. So that would mean that we're going to have 1 megahertz down here. And since mega means a million, that's 10 to the 6 hertz, right? And then we do our calculation. 3 times 10 to the 8 divided by 95.5 times 10 to the 6. And when I did that calculation, the answer I got is 3.14. And the units will be meters because the megahertz will cancel out here and here. 1 over S is the same thing as hertz, so that would cancel with that. So the only unit remaining would be the meter unit. So that would be the answer for number 1. All right. So that's the answer for number 1. That's a relatively simple exercise. Okay, the next question has to do with, let me see what it says here. Scroll down here. Okay, it talks about a laser and an audio compact CD player, which uses light with a wavelength of 7.8 times 10 to the 2 nanometers. So the question is asking for you to calculate the frequency of this light, and it's also asking for you to calculate the energy of a single photon of this light. Okay, so let me erase this here. Okay, so let's see here. So in this case, they gave you the wavelength and they're asking for the frequency. So it's going to be mu is equal to C over lambda, all right? C is always going to be 3.00 times 10 to the 8 meters per second. Let me close this. And you have to divide by the wavelength. So they gave you the wavelength as 7.80 times 10 to the 2 nanometers, but we have to convert from nanometers to meters, and nano means 10 to the minus 9, so 1 nanometer down here, and 10 to the minus 9 meters would be above, so that this will go with this, and the meters unit will cancel out. So your unit would be, your final unit would be seconds to the minus 1. So let me do this calculation here. 3 times 10 to the 8 divided by 7.80 times 10 to the 2, and then multiply by 10 to the minus 9. And according to my calculations, this works out to be equal to, round off to 365, so this would be 3.85 times 10 to the 14 seconds to the minus 1, all right? So that's basically how number 2 is done. Okay, let me see who is here. Okay, so 4 persons are here. Very good. Thought I was talking to myself for a while. All right, so any questions about either number 1 or number 2 that I've done so far? Any questions? Okay, so let's move on to question number 3. Question number 3. Oh, wait a minute. I'm not finished with question number 2 yet, actually, because question number 2 has a second part which says calculate the energy of a single photon of this light. So the formula for calculating the energy of a photon is right here. Whoops. E is equal to h nu. So let me squeeze that down here. E in this case would be equal to h, which is 6.63 times 10 to the minus 34 joules second, times the frequency that we just calculated here, which is 3.85 times 10 to the 14 seconds to the minus 1. So let me do that calculation. 6.63 times 10 to the minus 34, multiplied by 3.85 times 10 to the 14. And according to my calculation, this works out to be equal to 2.55 times 10 to the minus 19. And the units for this would be joules, because this will cancel out with this, all right? So that's the answer for the second part of number 2. Okay, any questions about that part? Any questions? Any questions? Okay, so let me move on to number 3. Excuse me. And number 3 says, you know what, let me just erase all of this here. Okay, so number 3 says microwave radiation has a wavelength on the order of 1.0 centimeters. Calculate the frequency and energy of a single photon of radiation. Okay, so in this case, the question is asking for the frequency and it gives you the wavelength. So therefore we can write down that frequency is equal to C over lambda, all right? Now C is always going to be 3.00 times 10 to the 8 meters per second divided by the wavelength, which is 1.0 centimeters, but we have to convert that to meters. So we're gonna have 100 centimeters down here, 1 meter up here. Centimeters will cancel out, the meters will cancel out, so your final units will be seconds to the -1 or hertz. So let me do this calculation here. 3 times 10 to the 8 divided by 1 divided by 100. So according to my calculation, this works out to equal to 3 times 10 to the 10. 3.0 actually times 10 to the 10. And the units would be seconds to the -1. All right, so that's basically how number 3 is done. Well, the frequency part and then the energy part, you're going to use this formula here. So H is 6.63 times 10 to the -34 joules second, multiplied by 3.0 times 10 to the 10 seconds to the -1. And let's see what this gives. So 3.0 times 10 to the 10 multiplied by 6.63 times 10 to the -34. And according to my calculation, when rounded off to 2 sig figs, this would give 2.0 times 10 to the -23 joules, because again, this will cancel out with this. So that would be the answer for the energy of the photon. And I think I repeated the question again, so, or that part of the question again. So that's basically how that is done. And then now for the B part, it's asking for the energy of Avogadro's number of photons. So basically what you have to do is multiply this here by Avogadro's number, because this gives the energy of 1 photon. All right, so 1 photon will give this energy. So therefore, to get the energy of an Avogadro's number of photons, what we do is multiply 2.0 times 10 to the -23 joules per photon, multiplied by Avogadro's number of photon, which is, of course, is 6.02 times 10 to the 23 photons per mole. All right. So therefore, this will cancel with that. And let's see here, 2 times 10 to the -23.
We can't see your writing.
Oh, sorry, my bad. Let me see, what am I doing wrong? Oh, it says you can't see my writing? Because according to the, can you see my screen at all?
I can see the problem, but I don't see you writing anywhere.
Oh, okay, all right, let me try something here. I don't know what, let me see here. Let me see. How is that?
Yes, I can see now.
Okay, good, all right. I'm sorry about that, folks. I didn't realize you weren't seeing what I was doing. Okay, do I need to go over this? Or is it clear enough for you? Anybody? Do I need to go over this? Okay, all right, so I'm just going to assume that you understand what's happening here, because I think it's laid out here pretty clearly, all right? This is the work for question number 3. All of what you see on the screen here is for question number 3. But I'm not finished yet because I need to multiply 2 times 10 to the minus 23 by 6.02 times 10 to the 23. And according to my calculations, rounded off to 2 sig figs, that would be 12 joules per mole. All right. So that would be the answer for the B part of number 3. All right. Okay. Any questions about this? Any questions? Any questions? Okay. Moving along. Okay. So number 4, it says the primary visible emissions from mercury occur at 404.7 and 435.8 nanometers. So the question is asking for you to calculate the frequencies of these emissions. So let me clear this again. And let me proceed to write down the formula that you're going to need, which would be the frequency is equal to C over lambda, right? So you'll be doing 2 calculations of the frequency, one for the wavelength at 404.7 nanometers. So we set this up as nu is equal to 3.00 times 10 to the 8 meters per second divided by the wavelength, which is 404.7 nanometers. And then I multiply that by, to convert from nanometers to meters, 10 to the minus 9 meters equal to 1 nanometer. So this cancels with that. This cancels with that. So the only unit remaining would be seconds to the minus 1. So 3 times 10 to the 8 divided by 404.7 times 10 to the minus 9. And the answer I got for this one is 7.41 times 10 to the 14. All right. So that's basically how we do that. And we do basically the same thing for the other wavelength. Same calculation, of course, different wavelength. So the wavelength in this case is 435.8 nanometers. And we multiply by 10 to the minus 9 meters over 1 nanometer. And we do the same number crunching. So 3 times 10 to the 8 divided by 435.8 times 10 to the minus 9. And the answer I got for this one is rounded off to 3 sig figs, 6.88 times 10 to the 14. All right, so that's basically seconds to the minus 1. So that's the answer for, I'm sorry?
Is that 431.8 nanometers?
I'm sorry, 435. This should be 5. My bad. I know my handwriting is not the best, so my apologies. 435.8, that's what it should be. Okay, any other questions about this particular problem? The A part for number 4? Okay, now for the B part, let me draw a line here. It says calculate the energy of a single photon and a molar photons of light with each of these wavelengths. So it's very similar to what we did before. For the energy of a photon, this is the equation we're going to use. So in the case of the first one, where this is the frequency, the energy of the photon would be equal to H, which is 6.63 times 10 to the minus 34 joules second multiplied by the frequency, which is 7.41 times 10 to the 14 seconds to the minus 1. So work that out. Okay, times 7.41 times 10 to the 14. Okay, so when I did that, the answer I got rounded off to 3 sig figs is 4.91 times 10 to the minus 19 joules. All right, 19 joules, right? So that's for this frequency. That's how we calculate the energy. And then for the other one, start off again with 6.63 times 10 to the minus 34 joules second multiplied by the other frequency, which is this right here, 6.88 times 10 to the 14 seconds to the minus 1. So let's do that. 6.63 times 10 to the minus 34 times 6.88 times 10 to the 14. And the answer I got for that one is 4.56 times 10 to the minus 19 again, joules, all right? So those are the energies of the photons of each of these wavelengths right here. And then finally, for this question, you're asked to calculate the energy of a molar photon. So that's similar to what we did before. In the interest of time, let me just go to another writing pad right here. So basically, we're going to multiply each of these energies. So the first one is going to be 4.19 times 10 to the minus 19. 4.19 times 10 to the minus 19. And this is the joules per photon. And we're going to multiply by Avogadro's number, which is 6.02 times 10 to the 23 photons in 1 mole. So these will cancel out. So let me do this calculation here. 4.19 times 10 to the minus 19 multiplied by 6.02 times 10 to the 23. And according to my calculation, this works out to be, when rounded off to 3 sig figs, 2.52 times 10 to the 5 joules per mole. And basically, you do the same thing for the other, let me see here, for the other frequency, which is the other energy, I'm sorry, which is 4.56 times 10 to the minus 19. So let me just do that down here. 4.56 times 10 to the minus 19 joules per photon. And it's the same thing as above, multiplied by 6.02 times 10 to the 23 photons per mole. And that's basically the setup. So let me do the calculation. 4.56 times 10 to the 19 multiplied by 6.02 times 10 to the 23. And according to my calculations, when rounded off to 3 sig figs, this is equal to 2.75 times 10 to the 5 joules per mole. All right? So that's basically how number 4 is done. Okay, any questions about number 4? Any questions? All right. So the next question is number 5. Okay, now this one requires a different equation. For number 5, the question says, let me make this, zoom this in. Okay, so for question number 5, it says calculate the longest and shortest wavelength of light emitted by electrons in a hydrogen atom that begin in the n equals 6 state and then fall to the states with smaller values of n. So let me try to draw a picture of what's happening here. This is basically based on the Bohr model. All right? Okay, what is happening here? Okay, I don't know what's going on with this. Let me zoom again. Okay, let me bring this down. And let me do this. Okay, so what the question is asking for is the energy required. Let's say that this is the n equals 6 energy level, right? Of the Bohr model, right? And you have other energy levels below that. You have n equal 5, you have n equal 4, you have n equal 3, you have n equal 2, and you have n equal 1, all right? So basically what the question is saying is that the electron is first here. So that's your electron. It's in the n equals 6 state, right? And the question is asking for you to calculate the shortest and longest wavelength as this electron falls from here to the other lower energy levels, all right? Now, if you remember, the equation which relates the energy gap between two energy levels and the wavelength is given by delta E is equal to hc over lambda, right? And if you recall, we said that there's an inverse relationship between delta E and the lambda. In other words, the smaller the energy gap between two energy levels of the transition, the longer would be the wavelength of the radiation that is involved, right? So basically what we need to do is calculate the longest and shortest wavelength, right? The longest wavelength would correspond to the shortest energy gap and vice versa. So let me just start off by saying well, another thing I need to mention before I even do that, the equation for calculating the wavelength as you go from one energy level to the other is this equation, 1 over lambda is equal to RH times 1 over NF squared minus 1 over NI squared. And we cannot forget the negative sign that should go before the RH here. So that's the equation we'll be using in this calculation, right? So for the longest wavelength, we have to look at the shortest energy gap starting with n equals 6. So the transition will be from n equals 6 to n equals 5, right? So what that means is that n final would be n equals 5 and n initial would be n equals 6, right? So we plug those numbers into this equation. We're going to end up with 1 over lambda is equal to minus RH, which in this case would be 1.10 times 10 to the 7 meters to the minus 1 times 1 over 5 squared minus 1 over 6 squared. All right? So we have to work this out. So of course we have to work out what's within the parentheses first. So let me see here. 1 divided by 25 equals minus 1 divided by 36. Okay, so the part in the parentheses is equal to 0.0 and 1, 2, and you have recurring 2's, right? So multiply by minus 1.10 times 10 to the 7 meters to the minus 1. So when I multiply that by 1.1 times 10 to the 7 equals, so the answer I get rounded off to 3 sig figs would be, 1.10 times 10 to the 7. Okay, I did something wrong here. I don't know what to do. So let me redo this part. 0.0122 times 1.10 times 10 to the 7. Okay, I knew I did something wrong. So let me erase this here. Okay, so the answer when I did this on my calculator would be, let me go back to the pencil function here, would be 1.34 minus 1.34 times 10 to the minus 10 to the 9. All right? Now, and this would be meters to the minus 1, right? Which means that lambda would be 1 over this, 1 over 1.34 times 10 to the 9 minus. So let me do that. Okay, so the answer I got for this part here is 7.44 times 10 to the minus 6, 7.44 times 10 to the minus 6, all right? Minus sign in front. And this would be meters, all right? Now, here's something that you need to take into account. You'll notice that there's a minus sign here, which comes directly from the minus sign here in the original equation. You might be wondering what's the significance of the minus sign, because of course, as you know, it should make sense to you that there's no such thing as a negative wavelength, right? So the interpretation of the minus sign is that this represents the wavelength of the light that is emitted, right? So the minus sign indicated that radiation is emitted. All right? So the actual answer to the question, because the question is asking for the wavelength of the radiation emitted. So the final answer would be lambda is equal to 7.44 times 10 to the minus 6 meters emitted. All right? So that's how we calculate the longest wavelength. All right? Okay, any questions about this? Any questions? Any questions about this particular problem? Any questions? Okay, now the other part is to calculate the shortest wavelength, which means, and I'm going to make some changes here, which means that to calculate the shortest wavelength, we have to look at the transition from hold on 1 minute, from n equals 6 to n equal 1, all the way down here. This is the n equal 1 energy level. So basically, we have to replace the 5 squared with 1 squared. So let me erase this here. So this 5 squared here will be replaced with 1 squared. That means that this number will be different. So let me erase that number here. So let me do that calculation. 1 minus, hold on, let me clear this. 1 minus 1 over 36. Hold on. 1 minus 36. Okay, so according to my calculations, this part here is equal to, oops, let me go back to my pencil function here. This part is going to be equal to 0.972, and they have recurring 2s. So when we do that part of it, let me erase this here. In fact, let me erase all of this down here. Okay, so back to my pencil function here. Okay, so let me do this now. So 0.97222 times 1.10 times 10 to the 7 equals, so I got here minus 1.07 times 10 to the 7 meters to the minus 1, which means that lambda is 1 over that. 1 over minus 1.07 times 10 to the 7 meters to the minus 1. So when I do 1 over that, the answer I got is 9.35 times 10 to the minus 8 meters. And again, there's a minus sign here. So again, that means that this is the radiation that's emitted. So therefore, the final answer is going to be 9.35 times 10 to the minus 8 meters emitted. All right. So that's basically how that is done. All right. Any questions about this? It's basically the same thing as what I did before. The only difference is that I switch from n equal 5 to n equal 1, and the calculation is the same right throughout. All right. Okay. So any questions? Okay, so let's move on to question number 6. And question number 6 says, calculate the de Broglie wavelength of a proton with a velocity 5.0, the speed, 5.0% the speed of light. So let me clear this up. And let me write down the Broglie equation, which is, oops, just do some water here, which is lambda is equal to h over mv, right? So we have to identify the different terms. It says what calculated the Broglie wavelength of a proton with the velocity of 5.c speed of light. There are a couple of ways we could actually do this. Let me see here. We may not have to use the Broglie equation. Well, let me use the Broglie equation. Okay, so first thing we need to identify is the mass of the proton. All right. So if you go to the tables I've posted in Canvas, let me see if I can find it. You will see that, let me go to files. Can you see my screen?
Yes.
Okay, good. I just want to make sure because sometimes when I make changes from one format to another, then some weird things happen. So let me download this. So in this table is included some information about particles like protons, electrons, and so on, the masses especially. So let me see if I can find it here. So, okay, is it here? Or is it here? Speed of light, Planck's constant. Okay, I thought, let me check up here. Nope. Or here. I thought, oh, you know what? I know where it is. It's on another sheet. I just remembered. Fundamental constants. That's where it is. Okay, so let me. Okay, mass of the proton. Where is it? Right here. 1.67 times 10 to the minus 27 kilograms. All right. So let me go back to. So the mass of the proton is 1.67. Before I forget it. 1.67 times 10 to the minus 27 kilograms. All right. So that's the mass of the proton. And then it says that the velocity is equal to, what is it? 5.0%. So 0.0050 times the speed of light, which is 3.0 times 10 to the 8 meters per second. So that is 0.05 times 3.00 times 10 to the 8. So that gives us 1.50 times 10 to the 7. So this is meters per second. All right. So we have the M and we have the V down here, and H is the Planck's constant. So basically we can calculate the wavelength. So the wavelength is equal to 6.63 times 10 to the minus 34 joules second divided by the mass, which is 1.67 times 10 to the minus 27 kilograms, multiplied by the velocity, which we calculated here, which is 1.50 times 10 to the 7 meters per second. All right. And again, we do our number crunching. So 6.63 times 10 to the minus 34 divided by 1.67 times 10 to the minus 27 times 1.50 times 10 to the 7. And according to my calculation, this works out to be equal to 2.65 times 10 to the 14. And the answer will be in meters. So that would be the final answer for question number 6. All right. Okay, any questions about this one? All right, so continuing. Let me see the next question here. Okay, number 7. I think, oh, there's one more after that. So there are 2 more questions. Okay. So let me get rid of this. And question number 7 says it takes 492 kilojoules of energy to remove 1 mole of electrons from the atoms on the surface of gold, solid gold. So the question is asking, how much energy does it take to remove a single electron from an atom on the surface of the solid gold? So basically, if it takes 492 kilojoules to remove 1 mole of electrons, then how much energy does it require to remove a single electron? So basically, we start off with the 492 kilojoules of energy per mole. So therefore, we know that 1 mole is equal to 6.02 times 10 to the 23 atoms. So we're talking about atoms here. 1 mole of atoms here and 1 mole of atoms here. All right. So let's do that calculation. 492 divided by 6.02 times 10 to the 23. And the answer I got when I calculated this is 8.17 times 10 to the 22 kilojoules per atom. All right, hold on. Minus 22, this should be, all right? Okay, so that answers the first part of number 7. The second part of number 7 is what is the maximum wavelength of light capable of doing this? So basically, you want to find out what the wavelength of light, which would have this energy, okay? So the formula we would use is E is equal to H nu. So nu is what we're trying to find, which is equal to E divided by H. Now the E that we're using is, of course, the 8.17 times 10 to the minus 22 kilojoules. And what we're going to do is divide by H, which is 6.63 times 10 to the minus 34 joules second. However, because we have kilojoules here and we have joules here, what that means is that we have to convert the kilojoules to joules, which means that we're going to have 1 kilojoule up here or down here, and that's equal to 1,000 joules, which would be the numerator above, so that this unit will cancel out with a kilojoule unit here. This joule unit will cancel out with this joule unit, so your final unit would be seconds to the minus 1. So 8.17 times 10 to the minus 22 divided by 6.63 times 10 to the minus 34 times 1,000. And according to my calculation, this works out to be equal to 1.23 times 10 to the 15 seconds to the minus 1. All right. And that's basically it as far as number 7 is concerned. Okay, are there any questions? Okay, give me 1 minute. I'll be right back. Ugh. Okay, folks, I'm back. So were there any questions for number 7? Any questions for number 7? Okay, so the last question in this set of problems, it says here the ionization energy of sodium is 495 kilojoules per mole. Will gaseous soda atoms be ionized by light with a wavelength of 589 nanometers? So it's kind of similar to what we just did. So let me clear this up and start off with what is given, which is the 495 kilojoules per mole. All right. Of atoms of sodium. I'm just going to use atoms here. So what we need to find out is how much energy would be required for one sodium atom. So that's where we use Avogadro's number, 1 mole of sodium atoms here over 6.02 times 10 to the 23 sodium atoms down here. And so this will cancel out this. So whatever this gives, this would give you the energy of required to remove 1 electron from 1 sodium atom. So let's work this out. 495 divided by 6.02 times 10 to the 23. And according to my calculations, this works out to be equal to 8.22 times 10 to the minus 22. And this would be kilojoules per atom, all right? So the next step is to find out the wavelength. So, well, in this case now, it's a bit different because in the case of the previous problem, they were asking for the, same thing, the wavelength, okay. But they asked for the energy, which is not asked for in this question. So things will be a bit different in this case because, okay, E is equal to H nu, right? But we know that nu is equal to C over lambda, so we can rewrite this as H C over lambda, all right? So we have the equation directly relating the energy to the wavelength. So the question is asking for the wavelength, so that would be equal to HC over E, and all we have to do now is put the numbers in. So H is 6.63 times 10 to the minus 34 joules second, times the speed of light, which is 3.00, times 10 to the 8 meters per second. And then we divide that by E, which is this number right here, all right? Which is 8.22 times 10 to the minus 22. And this would be kilojoules, but we have to convert it to joules. So we're gonna have here 1 kilojoule down here and 1000 joules above. And that's basically the setup. And all we have to do is to calculate 6.63 times 10 to the minus 34 times 3 times 10 to the 8 equal divided by 8.22 times 10 to the minus 32. Multiply by 1000. And according to my calculations, the wavelength calculated in this case is going to be equal to 2.42 times 10 to the minus 7. And the units will be meters because the joules will cancel with the joules here, kilojoules will cancel here and here, and the seconds will cancel here and here. So the only unit remaining would be the meter unit. So this would be the answer. All right. Okay, any questions about this one? Any questions? Any questions? Okay, so this is the final question in this series of questions. And as I said before, I thought it was important that we go through these so that you get a feel for the type of questions that you can expect to get in the future, all right? So, of course, I would recommend that you don't only just look at these questions, but you try to practice as many questions as you can from your different sources, your textbook, online sources, etc. All right? Okay, what I was planning to do for the rest of the class is talk about quantum numbers and atomic orbitals, right? Which comes directly from several topics that we talked about before, in particular when it comes to orbitals. So let me commence with this discussion. Let me ask you again, can you see what's on the screen?
Yes.
Okay, good. All right. So let's talk about quantum numbers and atomic orbitals. Now, we talked about the wave functions earlier. Of course, you know, at this level, you didn't need to go into the details. All you have to remember is that the wave functions basically lead to what we call the orbital of an electron in an atom, all right? It turns out that the wave functions contain what are known as quantum numbers, which are basically integral values, which are parameters which are needed to solve the Schrodinger equation. A wave function with a given set of these three quantum numbers is called an atomic orbital, all right? And these orbitals allows us to visualize a region in space where there's a high probability of finding an electron. So there are actually four quantum numbers, but we're going to talk about the three first quantum numbers first, and then I'm just going to make reference to the fourth quantum number. So the first quantum number is called the principal quantum number, all right? And it is symbolized by the letter N, and it should be lowercase n here, not uppercase. So please make a note of that, all right? Now, this quantum number is independent of the other two quantum numbers, all right? And it can only be a positive integer starting from 1, right? So 1, 2, 3, all the way to infinity, all right? And it turns out that the size of an orbital and its electron energy is dependent on the n value. So basically what you'll find is that as the n value increases, as the principal quantum number increases, the size of the orbital correspondingly will increase, and so will its energy, all right? And orbitals with the same value of n are said to have the same, or said to be in the same principal shell or energy level, right? So whenever you hear me use the term shell, it's basically the same thing as energy level, all right? Okay, the second type of quantum number, oh, by the way, before I move on to that, let me just say that it turns out that the orbitals with the same principal shell corresponds to the orbits in the Bohr model. But of course, we know that the Bohr model is not really workable. It doesn't work for multi-electron atoms, and that's why Schrodinger did his theoretical work, and that's how we get to the quantum numbers that we're discussing today, all right? Okay, the second quantum number is what is called the orbital angular momentum quantum number. In some textbooks, they call it the Azimuthal quantum number, and it is symbolized by the letter L. Now, the thing about this particular quantum number is that it determines the shape of the orbital. And there's some letter designation correspondingly for each quantum number of this type. So if L is equal to 0, the orbitals which have that quantum number, they're called the s orbitals. If L is equal to 1, then the orbitals that have that quantum number is called the p orbitals. If L is equal to 2, then the orbitals that have that quantum number they're called the d orbitals, and correspondingly, the f orbitals, the quantum number for those orbitals would be 3, all right? Now, the possible values of L is dependent on the n value, the principal quantum number, or the shell number, all right? So, and these are the ranges here. The possible values of L can range from 0 to n minus 1, where n is the principal quantum number, all right? So for example, if L is equal to 2, then the only possible values of L can be 0 or 1. And let me just do some other examples so that you have an understanding of what we're talking about here. So if L, write it here, if L, now remember, the values of L can go from 0 and all integers to n minus 1, all right? Those are the possible values of L. So if n is equal to 0, the only possible value of L would be 0. If n is equal to 1, then the possible values of L would be 1 and 0. If n is equal to 2, then the possible values of L would be 2, 1, 0. And if n is equal to 3, then the possible values of L would be 3, 2, 1, 0. And if L is equal to 4, then the possible values of L would be 4. Okay, I made a mistake here. Hold on. I made a mistake. Let me erase this here. Let me erase these numbers here. Because N can only start from 1. All right, so my fault. Let me correct this. N equal 1, N equal 2, N equal 3, N equal 4, N equal 5. Okay, so basically if N is equal to 1, L can only be equal to 0. If N is equal to 2, L can be equal to only 1 and 0. If N is equal to 3, then L is equal to 2, 1, 0. If N is equal to 4, L is equal to 3, 2, 1, 0. And if L is equal to 5, then L is equal to 4, 3, 2, 1, and 0. All right? And remember, there are some letter designations associated with these L values. So therefore, in the case of L is equal to 0, then basically we only have S subshells within, we have an S subshell within the N equal 1 shell. If L is equal to 1 and 0, so we're talking about S and P subshells. If N is equal to 3, we're talking about S, P, and D subshells. If N is equal to 4, L is equal to 3, 2, 1, 0, so that corresponds to S, P, D, and F. And then in the case of L equal 4, that will correspond to S, P, D, F, and G. All right, so those are the different designations for these corresponding L values, right? Okay. Any questions about this discussion so far? Any questions? Okay, going back to my slides. Okay, so how do we interpret these designations? Each of these orbitals is in a different region of space and they have different shapes, right? And all orbitals having the same N value and the same L value are said to be in the same subshell. So you hear me refer to subshells, the S subshell, the P subshell, and so on, all right? So these are the subshells that exist within the shells or energy levels, okay? Now, when it comes to the ML value, which is the third quantum number, that is called the magnetic quantum number. And it determines the orientation in space of the different orbitals, right? And the possible values of ML can range from minus L to plus L, all right? So just to give an example, if L is equal to 2, then the possible values of ML will go from minus 2 and all integers through 2, all right? Whoops, sorry. So that's basically how we can determine the possible values of ML. Let me just give you another example. So let's say L is equal to 3. Then the possible values of ML would be plus 3, plus 2, plus 1, 0, minus 1, minus 2, and minus 3. If L was equal to 1, excuse me, then the possible values of ML would be plus 1, 0, minus 1, all right? And so on and so forth, okay? So those are the corresponding ML values, and basically each ML value gives you some information about the three-dimensional orientation of the particular orbitals within that subshell in space. Okay, so to summarize what we have talked about here, we have this chart here, I'm sorry, which gives you basically everything that we discussed earlier. So just to recap a bit, for N equal 1, there's only one possible value of L, right? And there's also one possible value of ML. And what this means is that as far as the first shell is concerned, there's only one type of orbital, which is the S orbital, and there's only one of that type, all right, within the first shell. So that's the information that is conveyed here in the first shell. Now in the second shell, where N is equal to 2, there are two possible values of L, which would be 0 and 1. And as far as the ML values are concerned, there are 3 possible values of ML. So what that tells us is that within the second shell, there are 2 types of orbitals. The ones for which L is equal to 0, which would be the S orbitals, and the ones for which L is equal to 1, which are the P orbitals, right? And the fact that you have only one ML value here tells you that there's only one type of S orbital, which is designated the 2s orbital. And the fact that you have 3 ML values here tell you that there are 3 types of p orbitals, which are designated 2p orbitals, all right? And if you understand what I described here, then everything else here should make sense. In the case of the third shell, n is equal to 3. You have 3 possible L values, 0, 1, and 2. As far as ML values are concerned, for the first shell, it's only 0. For the third shell, I'm sorry, for the first, for L equals 0, ML would be equal to 0. For L equals 1, the ML values would be minus 1, 0, and plus 1. And for L equals 2, the possible values of ML would be minus 2, minus 1, 0, plus 1, and plus 2. So what that basically means is that in the third shell, you have 3 types of orbitals, S, P, and D, 1 type of S orbital, 3 types of P orbitals, and 5 types of 3D D orbitals. So therefore, we have 3S, 3P, 3 of them, and 5 3D orbitals present within the third shell. All right, and then, of course, based on what we have just discussed here, you should be able to describe what is happening within the 4th, 5th, and any shell that is beyond. All right. Okay. In terms of, what time is it? Okay, we still have time to talk about this. In terms of the 3-dimensional space or arrangements of these orbitals, right? In any case, electrons are most likely to reside nearest to the nucleus because, of course, the electrons are negatively charged and the nucleus has protons which are positively charged. So there will be some electrostatic attraction between those particles. Now, of course, as you go away from the nucleus, then the probability of finding an electron decreases. And that is what is being shown here. Now, this is a plot of the probability versus distance for a 1s electron, all right? So that's to be expected because as you go away from the electron, the likelihood of finding, as you go away from the nucleus, the likelihood of finding an electron decreases, as you can see. Now, what is used to determine the orbital is to find the probability of finding an electron within a particular space. And that's what this plot is all about. So this plot is 4 pi r squared times the probability of finding an electron. And you'll notice that the plot goes up to a maximum here and then it falls off. Whoops, falls off, right? So this gives you the actual 3-dimensional shape of the orbital. And in the case of the 1s orbital, this is what it looks like. It looks like a spherical shape, right? And this basically gives you a better picture in terms of, if you imagine taking pictures of an electron over different time periods and overlapping each picture, one picture, all the pictures over each other, you end up with this distribution, right? Which is basically giving you the shape of the orbital in the case of the 1s subshell, all right? So that's the shape of the 1s orbital. And in fact, all s orbitals have a similar shape, but there are differences. And to show that difference, I'm going to show you what happens in the case of the 2s orbital, which is spherical in shape. But the difference is that you have a region here where it's called a node. That's where the probability of finding an electron in that region is 0, all right? And that's a consequence of this plot right here, okay? So that's basically the shape of the 2s orbital. And what you're going to find is that as you go from one shell to the other, the next higher shell, when you compare their s orbitals, the number of nodes increases. So in the case of the 3s orbital, it's going to have 2 nodes. In the case of the 4s orbital, it's going to have 3 nodes and so on and so forth. And so that's as far as the shapes of the s orbitals are concerned. Then we have the p orbitals. And the p orbitals, as I said before, they come in sets of 3s. And this is what they look like separately. And you'll notice that they are aligned at mutual right angles. So if you're familiar with the 3-dimensional Cartesian system in math, you have, you have the x-axis here, the y-axis here, and the z-axis here, all right? And so one p orbital will be aligned along the x-axis as shown here. The second p orbital will be aligned along the y-axis, and the third will be aligned along the z-axis, all right? So this is what they look like separately. Collectively, this is what they look like, right? So this is the actual arrangement in any atom, in any shell beyond the first shell, all right? Where there are p orbitals, this is what they appear to look like, all right? And then we have the d orbitals, and as you can imagine, it's a more complicated situation. This is what they look like individually, and this is what they look like collectively, all right? To be perfectly honest, I don't expect you to memorize these. You do need to know the shape of the S and P orbitals, but these you don't need to know. You just need to know that they exist, and they exist in sets of 5s, right? And then you have the 7D orbitals, which would be in higher shells, which I won't even show you the diagram for that one. And then they increase exponentially as you go along. Okay, the final thing I'm going to talk about here is the 4th quantum number, which is called the electron spin quantum number. This will become important when we get to the next chapter, chapter 8. But basically, the electron spin quantum number explains some of the finer features of the atomic emission spectrum. Now, it turns out that when you have electrons in an atom, they can spin in one of 2 directions. So basically, their spin would be quantized, right? So they can spin, as you can see here, and the quantum number associated with this would be ms is equal to plus half, or the electron could be spinning in the opposite direction, where ms is equal to minus half. Now, you'll notice that there's an arrow here, where you have n and s at the tail and the point of the arrow. What that is showing you is the magnetic field that is generated when an electron spins, right? Now, I don't know how many of you have done any physics, but there is a rule known as a right-hand rule, which says that if you have a charge spinning in a direction which is corresponding to the fingers, if you hold your fingers, let me stop sharing my screen for a bit. Let me just show you something here. Okay, so this is my right hand, right? If the electrons are spinning in the direction of my, where my thumbs are pointing, that means that the magnetic field that is produced would be in the direction of my thumb. If my fingers are pointing this way, which shows you the direction of the electron spin, then the thumb is showing you the direction of the magnetic field generated, all right? And that is the right-hand rule that is used to predict the direction of the magnetic field based on the spin of the electrons, all right? So going back to, sharing my screen, going back to this page right here, if your thumb is pointing in the direction of the electron spin here, then the direction of the magnetic field from north to south is in that direction, pointing up. And that means that if the electron is spinning in the opposite direction, then the generated magnetic field will be pointing in the opposite direction, which is down, right? So the convention that is used in this context is that for the spin that is pointing up, or for the corresponding magnetic field generated pointing up, ms is equal to plus half, and for the opposite spin, ms is equal to minus half, all right? So that's basically the convention that is used, all right? So in summary, when it comes to the electron spin, the ms values, there are only 2 possible values that you have to worry about. And these values are not related in any way to the other quantum numbers that we talked about, all right? So that's the 4th quantum number, the electron spin. Okay, and this is just an experiment. I won't go into this, but this is the experiment which basically led to the discovery of the magnetic spins that is generated by electrons because of their, or the magnetic fields generated by the electrons because of their quantized spins, all right? Okay, so you can read up on that if you want to. It's not really terribly important at this level. Okay, so that's basically it for chapter 7, all right? So are there any questions you have for me? Any questions concerning anything that we covered today? Any questions? Okay, so if there are no questions, that's basically it for today. I'm contemplating posting, what would this be? Quiz number 4, I think it is. I'm going to post it online, and you have until week after next, because next week will be spring break, all right? So there'll be no classes next week. So you can look out for that assignment, and you can work on it. And I'll make sure include the deadline date for that assignment, all right? I don't think there's anything else I have by way of announcement. So that's pretty much it. Unless there are any questions you guys have. Any questions? Okay, if there are no questions, that's it for today. I'll be available for office hours today. Today's what? Thursday, so I'll be available from 11 a.m. to 5 p.m. today. If you have any individual questions that you don't want to ask me here and now, all right? So with that said, enjoy the rest of your weekend and also enjoy the rest of your, well, the spring break. And I'll see you Tuesday after next Tuesday, all right? So take care.
Good spring break.
I'm sorry?
Have a good spring break.
Well, I can hardly hear.
Have a good spring break.